Welcome friends. In today's lecture we are going to discuss failure theories for design under static loading conditions. There are five theories which are useful, and in this lecture we are going to discuss the first two theories. Those are maximum principal stress theory, or it is also known as Rankines theory, and second one is maximum principal strain theory, which is also known as Venant's theory. So let's start with the first theory, that is Rankine's theory. In this theory, the name itself suggests that we will be discussing only about the maximum principal stress, and also keep in mind this is also associated with one drawback, which is related to only principal stress. We will discuss it and also prove it in this lecture. So let us start. What is the statement for the Rankine's theory? It says that failure of mechanical component occurs when the maximum principal stress at any point in the body under complex loading condition reaches the yield or ultimate strength of the material in simple tensile test, that is we carry by using UTM, universal testing machine. Why yield or ultimate strength? Because if a material is a tensile, we know that it has a yield strength, and we consider that its failure point is at yield because here the material start yielding at the yield point itself. So if there is a plastic deformation after the yield point, so we can say that the component is not performing the desired function. So it is the condition where we can say the component has failed, and in case of brittle material, ultimate strength is considered as a failure point. Now let us consider this complex loading condition, or the actual condition in which a component generally occur, because even though we carry out the simple tensile test in uniaxial condition for finding the strength of the material, whether it is a ductile or a brittle material, but in actual there are actually different types of loads acting simultaneously on the component. So we will finally derive a equation and will compare it with the yield strength of the material first, and also we will prove that whether this theory is applicable for ductile material or not. According to statement, in short, you can say that principal stress should be less than the tensile yield strength, or we can say that if it is a brittle material, principal stress should be less than equal to the ultimate strength. Now consider the actual condition. We know that how we find the principal stresses. This is the formula for finding the principal stress: sigma 1 equal to, or sigma 2 equal to, sigma x plus sigma y by 2 plus minus under root sigma x minus sigma y by 2 bracket whole square plus tau xy square. In our complex loading condition, you know that if there is a shear stress acting on this plane, let us say this is a plane perpendicular to x-axis, then definitely this is not a principal plane, because at principal plane there is no shear, or shear stress will be zero. We have already proved or studied in previous lectures. So let us say at an angle theta there is a principal stress, and this will be the principal stresses, if we will consider in separate figure, sigma 1, this is the major principal stress, and sigma 2 is another principal stress. Considering the ductile material, you know that compressive yield strength and tensile yield strength are same for the ductile material under UTM. By Rankine's theory, what it says, sigma 1 should be less than equal to sigma y, that is yield strength, and also sigma 2 should be also less than equal to yield strength in both the tensile and compressive condition. So in compressive condition, you can write like this: sigma 1 should be less than equal to minus sigma y, or similarly sigma 2 should be less than equal to minus sigma y. Now we will write the equations for this condition. In short, all these 4, 1, 2, 3 and 4 condition can be written combinedly like this, and the separate equations will be like this: sigma 1 equal to sigma y, sigma 1 equal to minus sigma y, sigma 2 equal to sigma y, and finally sigma 2 equal to minus sigma y. Now we will put all these 4 equations on graph, and for that we will draw the first line for each equation. If we are going to draw a line for sigma 1 equal to sigma y, that means in this case sigma 2 is 0, and we are putting sigma 1 in on the x-axis. That means somewhere on the x-axis we will get a point showing the line or representing the line sigma 1 equal to sigma y. Let us say here we have got that point, and as the y component is 0, there will be a straight line perpendicular to x direction. Similarly, we will put or draw the lines for equation 2, 3 and 4, and we will get such straight lines, and finally we will find a closed region of the shape square, and this square shape represents the safe region in case of Rankine's theory or maximum principal stress theory. Now we will check whether this theory is suitable for ductile material or not. So considering the pure shear condition where there is no tensile or any other normal stress or forces applied on the component, consider this circular shaft subjected to the torque T. Applying the Rankine theory to this ductile material, what we will get? First of all, we will draw a pure shear component or the particle in this shaft, a smallest particle in this shaft, and we will represent it like this, having a pure shear condition. And we know that ductile material are weak in shear. So from Mohr circle, we will find the values for sigma 1 and sigma 2, that is principal stresses, putting the values of sigma x and y in this formula or the point C, which is the center. We know that sigma x and sigma y, that is normal stresses in the x and y direction, are absent. So we will put equal to 0, put them equal to 0, and here we have got the value for center, that is 0, 0. It is the origin of the coordinate system. Now we will find the radius for this Mohr circle by putting values of sigma x and y in this equation or formula. We will get r equal to tau, because sigma x and sigma y are 0, only shear stress will be present. So under root of this shear stress, square of under root of square of shear stress will be the simply shear stress tau. Now we will draw a circle having a center at the origin with radius tau, and we will get such a circle, Mohr circle. On this x-axis we will get the sigma 1 from the origin. This much region is the sigma 1, and from the origin to the left side there will be sigma 2. So as we know, the radius of the circle is tau, that's why value of the sigma 1 will be tau. For your convenience I will write here also, it will be tau. Okay, sigma 1 equal to tau, because you know the radius, value of the radius is tau. Similarly, sigma 2 will be equal to minus tau. Here we have got these values. Now we will check whether our condition is satisfied by the Rankine's theory, whether the theory is applicable or suitable or not. According to the Rankine theory, you know that sigma 1 should be less than or equal to the tensile strength, and also sigma 2 should be less than or equal to the tensile strength. So we know that sigma 1 is tau, and putting this value of sigma 1 in this equation, so we will get tau less than or equal to sigma 1, right? And let us assume that a material having a yield strength sigma y equal to 300 megapascal. So from that, if we will put this value of sigma y here, what we will get, tau should be less than or equal to 300, right? No, but experimental result says that for safe design of ductile material, the tau should be less than what? 0.57 times the sigma y. Here is the experimental value of the safe stress. That is the 0.57 times the sigma y value is the safe value for the shear stress. So, but here what we have got, the maximum value or safe value should be 171. If we will put the value of sigma y for our material, ductile material, let us say mild steel, and actually for safe design, tau should be less than equal to 171 megapascal. But in Rankine's theory, according to the Rankine's theory, what we have got, that sigma tau should be less than equal to 300, right? Tau should be less than equal to 300. So this is not matching. 171 is not equal to 300. So this theory is not suitable for the ductile material, as the safe value we are getting in the theory according to Rankine's theory is actually not safe experimentally, because experimentally the safe value should be 0.57 times the sigma y, that is here it is 171 megapascal. So even though it is not suitable for ductile material, but it is suitable for the brittle materials, right? And again, the another drawback is that as it only considers the principal stress and does not talk about the shear stress. Very first, in the beginning of the lecture, I told you, keep in mind the name of this theory, that is maximum principal stress theory. So it considers only the only principal stress, and in Rankine's theory equations we consider for design, it consider only the principal stresses, and nowhere there is a consideration of shear stress, and in such condition the material failed due to shear stress. That's why it is not suitable for the ductile materials. Now going to the next theory, that is the maximum principal strength theory. What this theory says? It says that for safe design, maximum principal strain in actual loaded component, that is component under complex loading condition, should be less than yield strain, that is the yield strain value of a particular material which we have got in the simple tensile test, that is under uniloadial condition in universal testing machine, right? Now similarly in this theory also we will define or evaluate the procedure as we have done in previous theory, and we will find out whether this theory is suitable for ductile materials or brittle materials. So very first we will find the equation for this statement. As we know that it is talking about the principal strain. So do you know how do we represent strain? We represent strain like this: epsilon x equal to sigma x by E minus mu sigma y by E minus mu sigma z by E. This is in 3D condition, and from this we can also write the equation in 2D condition. This is the component in actual loading condition, that is complex loading. As here is the presence of shear in the x plane, so this indicates this is not the principal plane. This plane is not the principal plane. This plane, okay, perpendicular to screen. So let us say or assume at an angle there is a principal plane. Here it is, let us say, principal plane where there will be no shear stress, and we can represent shear principal stresses in this principal plane like this. Let us say sigma 1 is the principal stress and also sigma 2, which are perpendicular to each other. This is the plane which we assume, right? Now we will write the equation in 2D from the equation 1. Epsilon 1 is equal to sigma 1 by E minus mu sigma 2 by E. Similarly, epsilon 2 equal to sigma 2 by E minus mu sigma 1 by E. Now let us define the yield strain in the simple tensile test. Let us say we are doing this experiment or carrying out this process of simple tensile test in UTM. So our tensile strain will be epsilon y equal to sigma y by E. Now applying this or putting these values in our maximum principal strain theory, according to that epsilon 1 should be less than yield strain and epsilon 2 should also be less than yield strain epsilon y. Here in 2D we can write epsilon 1 equal to like this, that is sigma 1 by E minus mu into sigma 2 by E should be less than equal to sigma y by E. So E is common in on the both sides, so we will cancel it, and the final equation which we are getting is sigma 1 minus mu sigma 2 should be less than equal to sigma y. We will use this equation for drawing the line on the graph and finding the safe region. So moving to the next slide. Similarly, sigma 2 by E minus mu sigma 1 by E should be less than equal to sigma y by E. That's why the another equation will be sigma 2 minus mu sigma 1 less than equal to sigma y. In case of compression, you know that both the yield strength in compression and tension are same. So epsilon 1 should be less than minus epsilon y. Let us say is compressive yield strength minus sigma y is the compressive yield strength, and similarly sigma 2 should be less than equal to minus epsilon y. I read it as epsilon as sigma. It is actually epsilon 2 should be less than equal to minus epsilon y. So the new equations will be like this. Instead of positive sign, there will be negative sign here and here. So collectively we can write the equation for this theory like this. Now we will write this equation separately for positive sign and negative sign. So the four equations which we will get will be like this: sigma 1 minus mu sigma 2 equal to sigma 1. Now we will write this, draw the lines or the whatever the graph or curve we are getting on the graph paper. You can say that we will get the straight line from this equation. So we will find the intersection of this line on the x-axis and y-axis by putting the value of sigma 1 equal to 0 and then sigma 2 equal to 0. By putting sigma 1 equal to 0, it is sure that we will get a point somewhere on the y-axis, right? Because the x coordinate we are putting equal to 0. So or what is happening, we have put the sigma x equal to sigma 1 equal to 0. So let us say this is the point x coordinate, and in this equation as we are putting sigma 1 equal to 0, we will get the value of sigma 2 which is equal to minus sigma y by mu. Let us consider mu equal to mu value equal to 0.3, which is in the range of 0.25 to 0.33. Because mostly metals have the value of mu in this range, we will put mu equal to 0.3. So we are getting the value for sigma 2 equal to minus 3.33 sigma y. Now putting this equation or the point on the graph, point A, let us say, as x coordinate is 0 and y coordinate is minus 3.33, somewhere here we are getting the point. Similarly, we will put value of sigma 2 equal to 0 in the same equation, this equation number 2. So what we are getting? We are getting the point B as sigma y comma 0. X coordinate is sigma y, let us say here it is sigma y, and y coordinate is 0. So we can say that this point is here on the x-axis. Now we will join these 2 points, and this green line which we are getting is nothing but the line or the graphical representation of this equation, right? This line. Similarly, we will draw all 4 lines, these green lines which you have seen. Let us say this is the second line and this is the third line, right? And this is the fourth line. So what we are getting, the shape of a rhombus. This is a rhombus. Keep in mind, this can be asked. The safe region in case of the maximum principal strength theory is the rhombus. Now for our convenience, we are comparing it with the Rankine theory. You know that in the Rankine theory, we have got a square shape. Like here you can see in the blue region, blue line, this was the safe region. So we will compare it with the Rankine theory. You can see here the rhombus, the boundary line of the rhombus. I will use different color here. Let us say yellow. Here you can see only this much portion is common in Rankine theory and maximum principal strength theory. So this region is safe in both the theory number 1 and 2. So this theory is suitable in case of where the values of this sigma 1 and sigma 2 are unequal, because here in this case sigma 1 is positive and sigma 2 is negative, where in this region both the values are positive, or also here also both the values are negative. Sigma 1 is negative and sigma 2 is also negative. But in these two regions only, the theory is convenient or conservative for the Rankine as well as the maximum principal strain theory, or it is also called as Venant theory. So you need not to get confused. Just you keep in mind, this is the safe region we are getting the rhombus shape, right? You need not to confuse with this square which we have got in Rankine theory. Just for your understanding or comprehension, I told that this is the common region in both theories. So if we will design a component by using the second theory, it will be safe in Rankine theory also, provided the values of sigma 1 and sigma 1 should be unlike. If those are like, let us say positive, then you will get a region which is not common. Here this much region is not common, so our component will be unsafe if the values of principal stresses are of having same sign. Let us say both are tensile and both are compressive. In such condition of a principal stresses, the Venant theory is not safe as if we will consider in comparison with the Rankine's theory, because this much region is not common for both these theories, right? Now we will find whether this theory is suitable in case of ductile material or not. Now applying the Venant theory to ductile material, again consider a material in pure shear and consisting of a ductile material, and you know that ductile material are weak in shear. So the smallest component in pure shear will be shown like this, and similarly, as we have find the center of Mohr circle in previous case, here also we will get a center as a origin here, and radius will be equal to the tau from this formula. So once again we are getting the values of sigma 1 equal to tau and sigma 2 equal to minus tau from this Mohr circle. If we will put a center of circle at origin, and by using this value of radius equal to tau, if we will draw a circle, we will get the values for sigma 1 and sigma 2. Now we have got this value, so we will compare with yield strength by using the Venant theory. For simplicity of calculation, we will assume mu equal to 0.3, which is in the range of 0.25 to 0.33. Generally, metals have a mu value in this range. Now, from this equation number 2, we will put in the value of mu and sigma 1, sigma 2, and we'll compare it with the yield strength. From the Mohr circle, we have what value of sigma 1 equal to tau and sigma 2 equal to minus tau. Right? We'll put these values in this equation. So what we will get? We will get tau should be less than equal to sigma y by 1 plus mu. That is, tau should be less than equal to sigma y by 1.3. And finally, tau should be less than equal to 0.77 times sigma y. But experimental result says that tau should be less than 0.57 sigma y. Then and then only the design will be safe. So, according to the experimental result, this theory is not suitable for the ductile material, because it is saying that even at higher stress than the 0.57 sigma y, it is safe. So, this theory is not suitable for ductile material. Alright. And similarly, it is also not suitable for brittle material. As we have seen, Rankine theory is suitable for brittle material, but this theory, St. Venant theory, is not suitable for neither ductile nor brittle material. So this theory is least used theory. This was all about the maximum principal strength theory. In next lecture, we will discuss about the remaining failure theories under tensile loading condition. And if you have any doubt, you can write in comment box. Till then, goodbye. Signing off for the day.